This is the 31st lecture, and we continue our discussion on lattice synthesis. In the 29th and 30th lectures, we talked about IIR realizations, various forms, direct, cascade, parallel, and in case of IIR parallel, actually you speed up the processing, because instead of a number of delays equal to the order of the transfer function, you can afford to use only 2 delays per channel, all right. So that the processing time, minimum processing time is no less, I beg your pardon, minimum processing time is twice the sampling interval. You have to add to this the time required for multiplications. Addition almost instantaneous, it is multiplication which is time consuming. Then we switched over to all pass IIR realization, and the first approach that we used was multiplier extraction approach. The aim was to make the realization canonic in multipliers as well as delays. Ordinary IIR direct form realizations do not achieve canonic multiplication. First order requires 2 multipliers, second order requires 4 multipliers, 4 or 5. Second order all pass 4, because in the denominator one term is unity, and in the numerator the coefficient of z to the minus 2 is also equal to 1. So, there are 4 multipliers. On the other hand, using the multiplier extraction approach, you can use 1 multiplier and 1 delay for the first order and 2 multipliers and 2 delays for the second order. That is the multiplier extraction approach. Next, we considered digital 2-pair extraction approach, again only confined to all pass filters. This approach leads to a modular structure, that is repeated structures in which only one parameter is variable, the k parameter, as we had identified. Each module called a lattice has only one parameter. Each lattice can be realized either with 2 multipliers or with 1 multiplier, a single multiplier, but for some reason, particularly historical and VLSI implementation, 2 multiplier realization is preferred except in dedicated programmable DSP chips like the tunable filters, for example. Okay. We will start with tunable filters today. If you remember, the 2 filters, one low pass and one high pass, first order filter of transfer function. I skipped an example. Shall we do an example first? Yes. Of a, okay. I had worked this out. Let's do the example, then we'll go to the program, to the tunable filters. I chose a second order one. I think this is one of the examples in the book. I don't remember what the number is. 1/8 minus 3/4 z inverse plus z to the minus 2, 1 minus 3/4 z minus 1 plus 1/8 z to the minus 2. So, if you wish to, it is an all pass filter, if you wish to realize by a lattice, you require 2 lattices in cascade terminated in a straight connection. Okay, y2 is equal to x2, that is the terminating condition. Now, obviously, the first lattice k2 is equal to 1/8. K2 is A2 of infinity, or In another manner, you can see the coefficient of the highest power term in the denominator, which is the same as this, but then you must make sure that the constant term is unity. Okay? You must make sure, this discipline you must follow. So, K2 is 1/8, it is less than 1. I also told you that if at any intermediate stage any of the k's comes out equal to or greater than 1, your job is simplified. You do not proceed further because the system becomes unstable, and an unstable filter cannot realize any useful job unless you design it to be so. An oscillator is an unstable system, but your purpose is to generate sinusoidal or other kinds of waveforms. Okay. To find out the other lattice parameter K1, you have to find out, from this you want to find out a A1z of the form 1 plus, let us say, D1 prime Z inverse, D1 prime plus Z inverse, and D1 prime would be equal to the recursion formula D1 minus D2 D1 divided by 1 minus D2 squared. D2 squared, do not make a mistake. Okay? 1 minus K2 squared, K2 is equal to D2. Now, you see an important feature, this is why I chose this example. Any example would have brought out this feature, that this is simply equal to D1 divided by 1 plus D2. Is that right? This shall always occur. Whenever you are going from the second order to a first order all pass, this shall always occur, and therefore your job is simplified, and since D1 here is minus 3/4 and D2 is 1/8, 1 plus 1/8, and this in my calculation comes as minus 2/3. I hope I am right. Okay? And therefore, this should be equal to K1, right? D1 prime is K1, and K1 is also magnitude is less than unity, therefore the system is stable. And once you have found K2 and K1, all that remains to do is to draw the filter, and as I mentioned to you earlier, I draw the filter is simply, I draw the lattice simply as a box, starting with, first you shall have K2, then you shall have K1, and the output is terminated like this. Pardon me? Put the values of K2 and K1. K2 is 1/8 and K1 is minus 2/3, where each of these boxes stands for a lattice of the form, you have two summers and then you have two multipliers. This is plus Km, this you must remember, plus Km in general, the mth order stage, and this one is minus Km. Minus Km. In addition to the lattice, you have a delay. This is a part of this block coming like this, and that is it. This is what stands for K sub m. This is what stands for the box marked K sub m. I am sorry, this is the arrow, this arrow goes out, this arrow goes out, this arrow comes in. We have compressed this into this form such that we do not have to draw this again and again. It is modular. This modularity leads to simplified fabrication in VLSI. Anything which is modular, if there is a structure which requires a processing steps change at every step, it becomes a very costly proposition. On the other hand, all that you have to change in the processing is the value of K for each stage, and therefore it is a suitable thing for VLSI implementation. All right. After this example, we consider First we consider the tunable low pass high pass combination. If you recall, the transfer function 1 minus alpha by 2, 1 plus z inverse divided by 1 minus alpha z inverse is a first order low pass filter HLPF of z, and its complement all pass as well as power complementary filter is the high pass filter HPF of z, which is 1 plus alpha divided by 2, 1 minus alpha z inverse, 1 minus z inverse. This is a high pass filter which the sum of the two is an all pass filter, okay, and they are also power complementary. They are also power complementary. That is, if I take HL e to the j omega magnitude squared, add it to HH e to the j omega magnitude squared, the sum shall be unity. These are doubly complementary filters. Sum is all pass and their magnitude squared sum is equal to unity. So, they are doubly complementary. And we also showed in our previous discussion that the low pass and high pass filters can be expressed as the sum and difference of two all pass filters, that is A0Z plus A1Z, and the high pass one is half A0Z minus A1Z, where A0Z is equal to 1, it is a straight connection, and A1Z is the first order all pass filter with the same denominator, that is 1 minus alpha z inverse, then you should have minus alpha plus z inverse. Okay. Therefore, the realization of one all pass filter, first order all pass filter, suffices to make a multi output system. One of the outputs is low pass and the other is high pass, and this is one of the most popular things in digital stereo. The low pass one goes to one channel and the other stereo channel is the high pass one. So, low frequencies and high frequencies are separated out, and that is what makes a stereo record. The implementation also we discussed earlier, because it is half sum and difference. So, we can realize the two filters like this, take the factor half out, which is a shift, no multiplication, and then you have two channels. You have two channels, one of them goes straight because the all pass function A0Z is 1. So, we shall have straight A0Z 1 feeds both the summers, then you shall have A1Z which feeds this summer half A0Z plus A1Z. So, this will be H of LPF of Z, and in order to create HPF you shall have to multiply by minus 1, which is not also a multiplication, it is a change in the sign bit. You see, this total thing is being realized by only a single delay and a single multiplier. If you choose to use A1Z with a single multiplier lattice structure, which is done because it is a dedicated chip, it is programmable only in alpha, nothing else. You require two functions, a low pass and a high pass, for splitting a given audio channel into its low pass, low frequency and high frequency components. So, the only thing that you change is alpha. What does alpha change? Alpha changes the bandwidth, and if you remember, the bandwidth is cosine inverse 2 alpha divided by 1 plus alpha squared for both the channels, and therefore, for A1Z a single multiplier lattice structure shall do, and this is available commercially as a programmable chip. Programmability only involves changing the bandwidth, the alpha. The structure is, let me draw it. I shall not draw it later. When I require to draw a lattice, I will simply put it in a box and put the reflection, put the k, the lattice parameter. Lattice parameter here is minus alpha. 1, you remember, in the denominator both of them have 1 minus alpha z inverse. So, the lattice parameter is minus alpha, then you have a summer, and the input comes here. If it is a single multiplier structure, this is what is V. Okay. So, x1 plus V, that gives you H, I beg your pardon, and the other one is a summer, the output comes here, then you have a Z inverse, and the output should be terminated in a straight line. Okay. It is a first order filter. This is the, if this is xz, then this is xz A1z. I have not shown the crisscross ones. This output comes here, and this goes here with a multiplication of -1. Yes, very good. With a multiplication of -1. This is the single multiplier lattice structure. Here we do not use 2 multiplier structure, okay, because I have to make it programmable. Making 2 multipliers shall mean that I have to adjust them independently, and they may not, after quantization, they may not be identical. If they are not identical, the all pass property is destroyed. All right. So, this is one of the structures for tunable filters. The other is tunable, once again is the same kind of thing, band pass and band stop filter. If you recall, band pass and band stop cannot be made with first order. The minimum order needed is second order, and the 2 transfer functions which we talked about was 1 minus alpha by 2. The denominator is the same, 1 minus beta 1 plus alpha z inverse plus alpha z to the minus 2. The numerator is 1 minus z to the minus 2. You remember why this 1 minus z to the minus 2 is there? To make, why is the numerator 1 minus z to the minus 2? To make the DC response equal to 0, and the response at pi, omega equal to pi also equal to 0. Okay. And now you shall appreciate why the denominator is written in this form, not 1 minus beta z inverse plus alpha z to the minus 2, because in the lattice realization of the all pass filter derived from here, let me write the band stop transfer function also, that is 1 plus alpha by 2, the same denominator, and the numerator is 1 minus 2 beta z inverse plus z to the minus 2. We shall show that these are also complementary, doubly complementary, all pass as well as power complementary. Okay. So, we shall show that these 2 filters can also be realized in a single chip using only one second order all pass filter, only one second order all pass filter with the denominator the same as this. Okay. And you will realize when we actually implement it, when you actually calculate the two lattices, you shall see that one of them has a parameter alpha and the other is beta. One is alpha and the other is minus beta. If you recall our discussion on these two filters, alpha and beta independently control the bandwidth and the center frequency. Center frequency in case of band pass is the frequency of maximum, and in the case of band stop it is the frequency of rejection. Okay? So, both of them, H BP of Z and H BS of Z, can also be written as the sum and difference of two all pass functions. But here, unlike the low pass and high pass, the band pass is the difference minus A1Z, A2Z, whereas the band stop is the summation of the two. Does this appeal to common sense? You may not have remembered, but the way to remember it is there is a negative sign here. It can come only from a difference. Okay? It can come only from a difference, and there is a positive sign here, so it comes from the sum. This is the way to remember that the band pass one requires a differencing and the band stop one requires an addition, where the two all pass functions are A0Z is 1 and A2Z is this all pass with the same denominator, that is 1 minus beta 1 plus alpha Z inverse plus alpha Z to the minus 2 alpha minus beta 1 plus alpha Z inverse plus Z to the minus 2. That is the band, that is the all pass filter that is required, and the structure would be very similar, half, and then you have two channels. You have an all pass filter here, A to Z, which now has to be multiplied by minus 1 to get H band pass filter, okay, and it is to be multiplied by nothing to get a band stop filter, BSF of Z, where A to Z obviously shall require two lattice sections. Let us see what these lattice parameters are. Okay, the lattice parameters. Now, the transfer function is, for lattice parameter we require only the denominator, numerator is known. So, D2Z is equal to 1 minus beta 1 plus alpha Z inverse plus Z to the alpha Z to the minus 2. So, K2 is equal to alpha. K2 is equal to alpha, and for finding K1 you have to find D1 prime, and if you recall, D1 prime would be D1 divided by 1 plus D2. Okay. So, D1 is minus beta 1 plus alpha. You recall why this formula? Yes. It is a simplified form. From second order to first order you can always use this simplified form. Okay. Minus beta 1 plus alpha divided by 1 plus alpha, that is equal to minus beta. In other words, what we require is a lattice with parameter alpha, the next one is a lattice with a parameter minus beta and straight connection. This transfer function is A to Z. Each of these boxes now has to be realized by a single multiplier structure. This gives you a programmable DSP chip weight two functional outputs, one is a band pass, the other is a band stop, and the center frequency can be controlled by one multiplier beta, which has to be programmable because you might like to change the center frequency, and the bandwidth is changed by alpha, and these are independent of each other. That is, when you change alpha, the center frequency does not change. This is the ideal situation. It is very difficult to attain this in analog filters. Okay? Digital filters totally isolate the bandwidth control and the center frequency control, and this is also available as a commercial chip. So far we have talked about only all pass filters. The question now that arises is, can these all pass filters, well, we have also used all pass filters to obtain a low pass, a high pass, a band pass and a band stop filter. Can the lattice realization of all pass filters be so modified to obtain a general transfer, general IIR transfer function? For example, let us consider a general transfer function. The denominator is 1 plus d1 z inverse plus d2 z to the minus 2. The numerator is not z to the minus 2 d z inverse, but it is a general numerator p0 plus p1 z inverse plus p2 z to the minus 2. Okay? Can it be realized by a lattice structure? That would make the lattice a more versatile structure rather than only being limited to all pass filters. Now, in order to realize this, what one does is the following. The first step is find out the corresponding all pass and realize this, that is 1 plus d1 z inverse plus d2 z to the minus 2, then d2 plus d1 z inverse plus z to the minus 2. The corresponding lattice structure, you now tap some of the outputs, and the tapping is done in the lower line. That is, you have input and output. You tap from here, you tap from, we shall have K2 to start with, then a K1, and then you have a straight connection. So, what you do is tap from here and tap from here. This is a realization of the all pass filter. In order to get a general filter, tap the outputs from the lower lines and weight them, that is, multiply this by alpha 1, this by alpha 2 and this by alpha 3 and add them together. Okay? Add them together. This is the philosophy that is followed, and this is now my output. This is all pass output and the required output is here. I have to satisfy three coefficients P0, P1 and P2, and I have used three weights here, alpha 1, alpha 2, alpha 3. What I shall do is I shall find out the output here, the numerator, and then match coefficients to find out the required weights alpha 1, alpha 2 and alpha 3. Okay. Let us carry this out completely, then we shall see how these coefficients, how these multipliers alpha 1, alpha 2 and alpha 3 are obtained. Is it logical that they would match? That is, we shall be able to get, is it guaranteed that we shall be able to get a numerator like this? I have three given parameters and I have to choose 3 unknown parameters. So, it should be possible. Degree, is the degree all right? I use 2 delays here and therefore, this is after 2 delays, this is after 1 delay and this is without delay. So, it should be possible. Second order, any numerator can be realized by using taps. Okay? Once we are sure it can be done, then we proceed. Let us see. The structure, now unfortunately I have to draw the total structure. Please draw with me. I can't do it boxes because I am going to analyze. The total structure that we are envisaging, well, first we draw the all pass structure, then we shall see the taps. Okay. X1, Y1, we have 2 summers and a Z inverse. Another summer, another summer. Draw with me. Okay? Another Z inverse, yes, very good. Another Z inverse is needed, otherwise we will not get a second order. Okay. And our multipliers are, first is minus D2, agreed, and this one is plus D2, this one is plus D2. And this multiplier is D1 prime. Okay. From the second order we go to the first order. So, this is D1 prime and this multiplier is minus D1 prime, let it come here, minus D1 prime, Z inverse, I have used everything. Okay. And I wanted to tap. Okay. Let us call this signal as S1, the signal available here is S1, the signal available here as S2, and the signal available here is of course Y1. Okay. Now, you know that Y1 by X1 is 1 plus D1, we took this second, yeah, okay, 1 plus D1 Z inverse plus D2 Z to the minus 2 and the numerator is D2 plus D1 Z inverse plus Z to the minus 2, this you know. Okay. Let us look at what is S1 by X1 and S2 by X1. Okay. As far as S2 is concerned, you see S2 of Z is the sum of 2 signals, one comes via this and the other comes via this, agreed? Now, this signal is obviously S1 D1 prime and the other signal is S1 Z inverse, that is it. So, S2 and S1 are very simply related, D1 prime plus Z inverse. What is this polynomial D1 prime plus Z inverse? It is the numerator of the first order all pass function, isn't that right? What is the relationship between D1 prime and D1 and D2? D1 by 1 plus D2. Both of these shall be useful as you will go through. It is a very beautiful derivation, first given by 2 gentlemen by the name Gray and Markel. This is a very elegant contribution to DSP literature, that a all pass lattice can be used to realize any arbitrary IIR transfer function, and you will see how things fit into place. Okay. So, we have realized we have established a relationship between S2 and S1. Let us find out what is S1. If you look at the figure, you can see that S1 is, how is S1 created? S1 has X1, okay. S1 is here. So, it is the output of this summer, output of the second summer is S1. Now, the S1 obviously is contributed by 3 signals. One is X1, the other is S2 Z inverse multiplied by minus D2, and the third one is S1 Z inverse minus D1 prime. Agreed? Okay. So, let us write this down. S1 is X1 minus D2 S2 Z inverse minus D1 prime S1 Z inverse. And we have already obtained a relationship between S2 and S1. Therefore, I can write this as X1 minus, well, this term, let me write it down first, D2 Z inverse S1 multiplied by D1 prime plus Z inverse. Agreed? I have substituted for S2 minus D1 prime S1 Z inverse. So, what I do is I take S1 terms to the left hand side. What do I get? S1 multiplied by 1 plus D1 prime plus D1 prime D2. There are 2 terms, D1 prime Z inverse. There is also a term here, D1 prime D2 Z inverse, okay, Z inverse, then plus D2 Z to the minus 2 is equal to X1. Right hand side there is a solitary figure X1. Therefore, S1 by X1 is equal to 1 divided by 1 plus, now what is this? Isn't this precisely D1? Okay. D1 prime plus D1 prime D2 is precisely D1. Therefore, we get 1 plus D1 Z inverse plus D2 Z to the minus 2. The numerator is 1 and the denominator is the same as that of the all pass function or the required function. Okay. So, S1 has the numerator equal to 1. Let us look at S2 now. S2 by X1 would be equal to S2 by S1 multiplied by S1 by X1, right. Now, S2 by S1 we already know, it is D1 prime plus Z inverse and the denominator is the same, plus D2 Z to the minus 2. All right. So, what is the numerator? Numerator is that of the first order all pass filter. Okay. Therefore, what we require now, if you use multipliers, let us call them arbitrarily as alpha 1, alpha 2 and alpha 3 and we add them together. I run out of space here. If we add them together, that is alpha 1 y1 plus alpha 2 S2 plus alpha 3 S3 divided by x1, all right, then it's okay. Alpha 3 S1. Thank you. Alpha 3 S1. Yes. The denominator shall be the same. 1 plus d1 z inverse plus d2 z to the minus 2. The numerator n of z shall be alpha 1 times y1. So, alpha 1 times d2 plus d1 z inverse plus z to the minus 2. Agreed? Alpha 1 times the numerator of y1. Numerator of y1 is simply this with coefficients reversed, plus alpha 2 times the numerator of S2, that is d1 prime plus z inverse, plus alpha 3 times the numerator of S1, which is 1. Agreed? This is required to be equal to P0 plus P1 z inverse plus P2 z to the minus 2. Now we match coefficients to be able to get the required multipliers. Obviously, okay, let's match the coefficients and let us see what they come out to be. Obviously, P0 should be equal to alpha 1 d2 plus alpha 2 d1 prime plus alpha 3. P1 should be equal to alpha 1 d1 plus alpha 2, and P2 should be equal to alpha 1. Now, don't you see the solution is extremely easy? You can go from the last one, alpha 1 is equal to P2. Since you know alpha 1, you can now find out alpha 2, and since you know alpha 1 and alpha 2, you can find out alpha 3. Okay? And the results are, if you solve this, alpha 1 equal to P2, no matrix inversion is needed, because the size of the equations reduce as we go ahead, and the last equation has only one term on both sides. Okay? So, alpha 1 is P2, alpha 2 is P1 minus P2 d1, alpha 3 equal to P0 minus P2 d2 minus d1 prime, that replace it by d1 divided by 1 plus d2, but you have already found out d1 prime, so you know the number. Okay? d1 prime P1 minus P2 d1. So, any arbitrary IIR filter can be realized with all pass lattice. Lattice in that sense is a very versatile. The lattice is a structure of a versatile element called an all pass filter, and that is why all pass filters, DSPs has obsessions with all pass filters. Just quickly, if you have a third order transfer function, P0 plus P1 z inverse, I have taken the simplest second order. If you had the third order function P2 z to the minus 2 plus P3 z to the minus 3 divided by 1 plus d1 z inverse plus d2 z to the minus 2 plus d3 z to the minus 3, then you would have realized the lattice with 3 parameters, d3, d2 prime, yes, d1 double prime, and then straight connection. You take now tappings from here, call this alpha 1, from here call this alpha 2, from here call this alpha 3, and from here call this alpha 4 and add them together. Okay. can you by observation and by looking at the second order realization, can you tell me what these signals would be? Let us call them S1, S2, S3, and this is of course Y1, this is X1. Can you tell me? The numerator of S1 shall be 1, denominator is the same. Numerator of S2 would be first order? Yes, that is D1 double prime plus Z inverse, and for this it would be second order, D2 prime plus D1 prime Z inverse plus Z to the minus 2, and Y1 of course is the total thing, D3 plus etc. Okay? D3 plus D2 Z inverse plus D1 Z to the minus 2. So, you can find out the required coefficients alpha 1, alpha 2. Please do verify that these coefficients are alpha 1 equal to P3. Okay, I am now going the other way around. Alpha 2 is equal to P2 minus alpha 1 D1. Alpha 3 equal to P1 minus alpha 1 D2 minus alpha 2 D1 prime, and alpha 4 is equal to P0 minus alpha 1 D3 minus alpha 2 D2 prime minus alpha 3 D1 double prime. These are the coefficients, these are the multipliers that are needed. We shall work out an example of a general filter, general transfer function, and this example I have chosen intentionally. I am going to use this later also for some other examples, so that the results here can be utilized later also. This is 6.44C in Mitra, and it says realize this by a Gray-Markell structure. The structure itself is known as Gray-Markell, not the all-pass one, but the tapped all-pass one, tapped and summed all-pass one. It is given as 1 plus 3/4 Z inverse plus half Z to the minus 2 plus 1/4 Z to the minus 3, and the numerator is 2 plus 5 Z inverse plus 8 Z to the minus 2 plus 3 Z to the minus 3. The first thing to do is to realize an all pass filter with this denominator and the numerator Z to the minus 3 D3 of Z inverse, okay, all pass filter. Now, you do not have to write all this, because you can see that for the all pass K3 is 1/4, okay. Then you have to find D2Z, okay. In finding D2Z, your coefficients are D2 prime would be equal to D2 minus, yes, D3 D1 divided by 1 minus D3 square, and that comes out as 1/3, my calculation. D1 prime is equal to D1 minus D3 D2 divided by 1 minus D3 square, that comes out as 2/3. Therefore, you do not have to write the all pass function, just write the denominator. D2Z is equal to 1 plus 2/3 Z inverse plus 1/3 Z to the minus 2. Therefore, K2 is equal to 1/3, which is also less than 1. If at any point it comes equal to 1 or greater than 1, you say it is not possible. Okay. So, K2 is equal to 1/3, And finally, in calculating d1z, all that we have to find out is d1 double prime, and this you know is d1 prime divided by 1 plus d2 prime. That is equal to d1 prime is 2/3 divided by 1 plus 1/3. So, this is equal to half. Therefore, K2, you do not have to write d1z, K2 is simply d1 double prime, K2 is equal to half. I beg your pardon, K1 is equal to half. And therefore, I can write my lattice as 1/4, the next one is 1/3, and the next one is half. This is the lattice. The next job that I have is to calculate alpha 1, alpha 2, alpha 3 and alpha 4. Then add them up. This is my real output. And if you apply the same trick or the formulas that we have derived for the third order, my results come as alpha 1 comes as 3. Please do verify this. Alpha 1 comes as 3, alpha 2 as 5.75 and alpha 3 as minus 1/3, alpha 4 is minus half. This is my result by comparing the numerator with the given numerator or by applying the formulas, because all the coefficients you have calculated. Now, in these multipliers, the only source of problem is this multiplier minus 1/3, because whatever way you quantize it, you are going to have error. On the other hand, half is no multiplication, 5.75 is no multiplication. Why? 5 is 4 plus 1 and 0.75 is 3/4, half plus 1/4. So, shifts, this shall be done in parallel. Okay. 3 is no problem, 2 plus 1, agreed. So, you shift one channel, you shift, on the other one you put it directly. That is how. So, minus 1/3 is a problem. If it could be avoided, we would have been happy. Okay, this leads us now to the question how to, we have tackled IIR filters, and since lattice is so favored structure, so much a favored structure, what about FIR? Can we realize an FIR filter also by a lattice structure? Now, it is a historical fact that FIR lattices were not synthesized, they were synthesized by analysis, and we shall follow the same procedure. Do you understand the methodology? You see, synthesis can be done ab initio, that is, we do not know the structure, we try to get the structure, as we did in the case of IIR lattice, starting from what? Digital 2-pair extraction approach. Okay? So, there was an approach that we used, we did not know the structure. Here, traditionally and historically, we start from the structure, analyze it, then compare with the given requirement and match things. This is called synthesis by analysis. Okay? For example, if you want an analog band stop filter, second order, then you know various structures that use, for example, a parallel T network. So, you draw the structure and then match the coefficients or the values of the resistors and capacitors so that you get the this is called synthesis by analysis. So, we will follow synthesis by analysis for the FIR structure. I would like you to draw with me. I will first draw the complete structure for a transfer function HMZ equal to 1 plus summation FIR. So, there is no denominator, Hn z to the minus n equal to 1 to capital M. Capital M is the order of the filter, and our discipline that the constant term we shall always take as 1. Okay. The structure looks like this. Please draw with me. It is a, because it is FIR, there should be no feedback. It should be a non-recursive structure. So, we start with an input x0, the notations also change. I will tell you the reason a little later. Then x0 is the same input is delayed by one sample, and then the lattice starts. The lattice is like this, summation, here also a summation, and there is a crisscross now. The two multipliers should be all in the forward direction, no feedback, no recursion. This is K1 and this is also K1. This is the basic module. Okay? The basic module is that both lines go in the forward direction, the multipliers also go in the forward direction, but in a crisscross manner, and the difference between IIR lattice and FIR lattice is that the two multipliers are identical. Okay. This can also be realized by a single multiplier structure. It requires a little bit of innovation. Now, these two outputs, now we shall call them x1 and x1 prime. Both of them shall be useful. Okay. Both of them shall be useful. Therefore, we will take x1 and x1 prime. One thing that I forgot to mention in the IIR structures, general IIR structure or the all pass IIR structure, is that if you fabricate a chip and take outputs from S1, S2, S3 and so on, this becomes a multi-function chip. Isn't that right? For example, S1 by X1 is an all pole filter. The numerator is 1. S2 by X1 has 1 0 and m number of poles. So, it becomes a multi-function, and this is the beauty of DSP, that one chip can perform a variety of functions.